So continuing on our discussion of two-dimensional motion, we need to talk about vectors. Now in the previous example, in the previous video, we had an object move in the x direction and the y direction, that two-dimensional motion, and we're able to use the Pythagorean theorem to figure out what direction and magnitude the resulting vector was. Sometimes it's not that easy. In fact, most of the times it's not that easy. So we need to talk a bit more about how to appropriately add vectors together. And we're going to start off by doing a graphical analysis, which is not as quantitative as the subsequent video we'll talk about, but is still a useful tool on how to combine vectors. So again, vectors are quantities with both magnitude and direction. You can represent them with an arrow, but those arrows are drawn in a very certain way. One, the direction of the arrow, of course, is the direction of the vector. Right? Vectors have direction, up, east, northeast, down and a little bit south, whatever the direction of that displacement, velocity, acceleration, whatever. So the direction of the arrow has to be pointing in the direction of the vector. Secondly, the magnitude of the vector is represented by the length of the arrow. And that's a bit arbitrary in that you don't have to have an arrow 1 mile long in order to represent a displacement of a mile. But when you're combining vectors, as we're talking about adding them together, their relative sizes have to be the same. So if you draw a vector 1 inch, approximately 1 inch long that represents a mile, a vector 2 miles should be 2 inches. A vector 5 miles should be 5 inches, and so on. They have to have the same scale, or this addition doesn't work. Now, multiple vectors of the same type can be added together graphically or analytically, and we'll talk about, again, analytically in the next video, which is a more appropriate way of doing it. But graphically, it helps intuitively, you see how these vectors work together. Well, they have to be the same type, right? You can't add together displacement and velocity vectors. You can't add together acceleration and velocity vectors. They have to be the same type, just like you can't add together hours and degrees, right? You have to have the same unit to add things together. And finally, when you do add these vectors, analytically or graphically, it doesn't matter what the order is. It doesn't matter which, if you have 5 vectors that you're adding, it doesn't matter if you add them in order 1, 2, 3, 4, 5, or 5, 4, 3, 2, 1, or 2, 3, 1, 4, 5, or whatever you want to do, because vector addition is commutative. And if you remember back to your algebra days, commutative simply means a plus b is equal to b plus a. You can switch them around. So in this example, we're going to look at adding 3 vectors together. And the way to think about it is, for displacement, kind of like you're reading a pirate treasure map. So you start at the old broken log, and you take 100 steps due north, and then take 50 steps due east, then turn southwest and take 40 steps, then X marks the spot. Well, what if you don't want to do all that? What if you know math and you know physics, and you're like, I'm just going to add these vectors together and figure out where I need to go and what I need to do in order to just walk right to the treasure from the old broken log? Well, so what single vector can replace these 3? Well, I've drawn out the 3 vectors here using my handy ruler and protractor. So north is easy, of course. North I've defined to be up, south is down, east is to the right, west is to the left. So north is just straight up. The length of this vector represents 100 steps. I just have that being 10 centimeters on my giant protractor here. The second one is shown in blue, 50 steps to the east, and then southwest, or 135 degrees from the positive x-axis, going clockwise. So down and to the left, right, halfway between south and west, with a length of 40. So what single vector can replace these 3? I'm going to use the graphical addition method called the head-to-tail method. In this method, we simply start off at some point and then add the vectors head to tail. So here's our starting point. Here's that old log I was talking about. Now we can add them in any order. I'm just going to add them in the order that we have shown in the problem. So starting here, we go 100 steps to the north. Now, ending at that vector, the arrow of that vector, I attach the tail of the next vector. So if I could slide this vector over, I'm going to do this by hand, so it's going to be a little crude. But I'm going to slide this vector over. Now, attach the head of that vector, the tail of the next one. Drawing this here. Put a dot there so I know which direction I'm going. And the length has to be 440. So I've attached those three vectors together. And you can see my ending point is here, right? There's X. That's where the treasure is. I put a big red dot here. So rather than doing all of that, I can simply connect my starting point to my ending point. Erase that big dot here. And I've created this red vector, which I'll call D, because we have vectors A, B, and C already. So that vector D is all I need to do in order to properly go from the starting point to the treasure. But graphically, I have to measure it yet. So it is approximately 76 steps. And then figuring out the angle at 20 degrees east of north. So if I have north being 0 degrees straight up, I just need to move 20 degrees east of north, 76 steps, and I'll get to the same location. Again, there's a little bit of error in here because this might not be perfectly horizontal or vertical. This might not be perfectly horizontal. I might have gotten the lengths a little bit wrong with this crude ruler. So there's a better way of adding these analytically, which we'll look at in the next section. But I just want you to understand what the head to tail method of vector addition is graphically. Now we've talked about graphically adding vectors. What about subtracting vectors? Well, like algebraic subtraction, it's just addition of a negative number. Right? So it's the same as adding a negative. Just like 5 minus 3, you can rewrite that as saying it's 5 plus a negative 3, which is equal to 2. So these are algebraically the same. So since vector addition is the same thing, if vector C is vector A minus B, it's the same as adding A to vector negative B. So we could still add the vectors, head to tail method. We just have to figure out what I mean by negative B. Well, vector negative B is the same magnitude as vector B. It's just pointing in the other direction. So the negative of a vector is just that vector flipped. So vector B here has some length going up and to the right. Vector negative B has the exact same length going in the exact opposite direction. So if a displacement vector is down, the negative of that displacement vector is up. If it's to the east, the negative of that displacement vector is to the west. But the magnitude is the same. So if you have to subtract two vectors, figure out which vector you're subtracting, flip it around, flip the direction around, and then add it. Finally, in the last part of this video, we're going to talk about multiplying scalars and vectors together. Now vectors, there are actually three different types of multiplication for vectors. You can multiply a vector by a vector. You can multiply, it's called a cross product. You can multiply a vector by a vector in what's called a dot product. And you can multiply a scalar with a vector. We're just going to focus in on this last one for now. So when you multiply a scalar with a vector, The scalar has the effect of changing the magnitude of the vector, unless that scalar is 1. Multiplying anything by 1 doesn't change it. So the direction of the vector remains the same if the scalar is positive. If the scalar is negative, the direction flips, like we just talked about with b and negative b. So, an example here, if the scalar a, if a is just equal to negative 2.5, now a is a scalar, so there's no direction information there, it's just the number negative 2.5. If b is a vector, and that's 10 miles north, so it's a displacement vector, north 10 miles, when you multiply the scalar by the vector to get your new vector c, the result is a vector. The result has direction, the result has magnitude. You just multiply the two numbers together, you will get negative 25 miles north, but that's the same as 25 miles south, right? The direction changes. So multiplying the vector 10 miles north by negative changes the vector direction to south. The magnitude of a vector is always positive. The direction is what changes. And so if you multiply the vector by a number greater than 1, the number will get larger. If you multiply the vector by a number between 0 and 1, the vector will get smaller, right? If I multiply it by 1/2, then this will be 5 miles instead of 10 miles. So this is how you multiply scalars and vectors.